to infinity and beyond. Or let's just take some limits and see that we're going to be approaching infinity in some of them. Let's go. So we're asked here, does the limit as x goes to 3 of 4 over x minus 3 exist? So that's one of the main questions here. So let's take a look at this. Now to understand it, we're going to use the graph as well as a table to understand what's going on here. So both graphically and numerically, we're going to take a look at all this. So first things first, let's start out by just plugging in some numbers around 3 to figure out if the limit exists. So we're essentially finding if the limit exists as we approach 3 from the left and 3 from the right side, and then we're seeing what those values are. So I'm going to plug in numbers getting close to 3 from the left side. So that would be something like 2.9, 2.99, and then you guessed it, 999. And we'll plug those into 4 over x minus 3 to see what we get as we approach 3 from the left. Approaching 3 from the right would be something like 3.1, 3.01, and 3.001. So that gets very, very close to 3 from the right side. Okay, now I've already plugged those numbers into my calculator. You could do the same. 2.9 plugged into 4 over x minus 3 gives me negative 40. 2.99 plugged in gives me negative 400. I'm looking down because I've got it on my calculator. Here it is, right here. So from there, I plug in, let's see, 2.999. And that gives me negative 4,000. Ooh, this number's getting really big considering we're not really moving very far in the x direction, but moving very far in the y direction. When I plug in 3, I get an error, which makes sense because if you plug 3 into this, you get 4 over 0, which is undefined. 3.1 plugged in gives us 40. 3.01 gives us positive 400. And then 3.001 gives us a positive 4,000. So what we see here is that as we approach 3 from the left side, we get more and more negative and quickly. And as we approach 3 from the right side, we get more and more positive and just as fast as we did from the left side. So does the limit exist? Well, first of all, the answer is no, right? And the reason being is the limits are different from both sides. The limit as x approaches 3 from the left goes towards negative infinity. Now, even though we say negative infinity, that's the same as saying the limit doesn't exist. We're just saying to what infinity we're traveling. So how's the limit acting? It's going down really fast, and the limit doesn't exist. The limit as x approaches 3 from the right of the same function, that approaches a really, really positive infinity, super positive infinity. Not that there's such thing as super positive, but that still means the limit doesn't exist. So if your limit goes to infinity, your limit does not exist. But a lot of teachers will have you state infinity or negative infinity so that you're able to go a step further in describing in what direction are we traveling. We're traveling on and on forever upwards or on and on forever downwards. And you see here from the graph that we've got a vertical asymptote here at x equals 3. And what's happening is as we approach from the right side of 3, we're going up infinitely much, and from the left side down infinitely much. That's it. That's what it means to have a limit go to infinity. So we're going to look a little bit more in depth into this and see why this is happening. Notice that you get 0 in the denominator and a constant up in the numerator, causing us to rocket up and down like that. Okay, so let's use the graph now to find these limits, do a little more exercise. So we've got f of x equals negative 1 over the quantity x minus 2 squared. Well, we're going to find the limit as x goes to 2 from the left side of 2 of f of x. So that'd be from this direction here. And as we come from the left side, oh Nelly, we go down and fast. So again, even though I'm saying we are equal to negative infinity, that's the direction we're going in and where we're going to travel to. The limit technically still does not exist. Very important there. The limit as x approaches 2 from the right side of 2 of f of x. Well, here we are also going down to negative infinity. Does that mean that the limit doesn't exist? Sure, it still doesn't exist. But now what we can put here is we can put that the limit does approach negative infinity no matter what side we approach from. Remember, with no plus or minus, we're asking what y value do we approach from both sides of 2. We approach negative infinity. Yes, the limit still doesn't exist, but we can at least agree in what direction it's going in. It's a little different from the first problem we talked about where, well, we couldn't agree. From the left side we went down and right side we went up, which is why the limit did not exist. All right, so let's go on to another problem. This says, you've seen that we've been working with vertical asymptotes now. Find the vertical asymptotes of each function. I want us to be able to do that without a graph. So when does this happen? Well, essentially, a vertical asymptote happens when a graph goes up really fast or down really fast to infinity and acts like a vertical line. When does that happen? Well, we've seen now from the numbers we plugged in on the first problem we looked at, that occurs when we've got a number over 0, so a non-zero number over 0. So I set x plus 2 equal to 0, and I solve. The reason why I'm setting it equal to 0 is that's giving me the x value that will make the denominator 0. So x equals negative 2 is my vertical asymptote. It makes the denominator 0 and the numerator not 0. To understand a vertical asymptote for g of x, well, there's a lot of them. I'm going to rewrite g of x as the sine of x over cosine of x. What will make a vertical asymptote happen here is when the denominator is 0 but the numerator is not. Well, that would be the same as saying, when is cosine of x equal to 0? So I set it equal to 0. And this one's tough because cosine of x has infinitely many places where we're equal to 0, right? If you think about cosine of x, it's going to just keep going on and on and on and on in both directions. So we're going to equal 0 here and here and here and so on and so forth. So that's going to happen at x equals pi over 2. That's the first time starting at 0 that happens. Plus, and what we can then put is every pi that we add on to this or subtract from pi over 2 will land us at the next place where cosine is 0. So that's going to be plus pi n. Some people use k, where n's any integer. So that would be all your vertical asymptotes, right? Pi over 2 plus, we keep going around if you need to look at it on a unit circle. Pi over 2, go another pi. 3 pi over 2, go another pi in any direction. That adds that pi amount that we rotate around the circle. All right, last but certainly not least, we've got h of x equals x over x cubed minus x. I think it's actually important here that we factor this out because we don't want to call something a vertical asymptote when it isn't. So I factor out a greatest common factor from the denominator, x. That gives me x squared minus 1. So first thing to notice here is these two x's divide out. And from our studies with continuity and non-removable versus removable, we know that's a removable discontinuity, a whole at 0. So this gives us the function 1 over x squared minus 1, and x cannot be equal to 0. So we don't have a vertical asymptote at x equals 0, that's a whole. What we can do, however, though, is say, wait a second, I will get 0 in the denominator, and only in the denominator, when x equals 1 and when x equals negative 1. Either of those values when squared, and then subtracting 1 from it, will give you 0 in the denominator. So in general, how can we determine if and where a function has a vertical asymptote without graphing? Well, basically you set the denominator equal to 0. Set the denominator equal to 0. And solve. But a big piece of information there is that the numerator cannot equal to 0. That is very, very important to note. Okay, last but certainly not least, I wanted to point out the graphs of what we just looked at here. So if we take a look at the graphs, we now have the graph that we just put out there, negative 7 over x plus 2, tangent of x, and then x over x cubed minus x. Notice we've got our vertical asymptote as we found here at negative 2. We've got our vertical asymptotes every pi distance away. So we have negative pi over 2, pi over 2, 3 pi over 2. Corresponds with what we saw on the last slide. And then here we got a vertical asymptote at negative 1 and 1, but a whole at 0, at x equals 0, not a vertical asymptote. So that's it. I thought it would be good and worth our while to see how our numerical answers corresponded with our graphical. I will see you on the flip side.